Hi. Hi. Thank you for coming. This is Intro to Algorithms. My name is Young Che, and yeah, cool. Algorithms. Let's get started. So, what is an algorithm? I'm gonna have to start at the basics here. Algorithms, basically a function. Um, I'm sure we did all this back in algebra and all that. Fx is 7x. Uh, F4 is 28. So the definition I found was that a set of rules to obtain the expected output from the given input. So if we put 4 in fx is 7x, we expect 28 and we get 28, right? That's what an algorithm is. For CS majors, I'm sure this is more familiar. F list is sorted list. Yeah, this is this is mainly what we use for algorithms, right? If statements, arithmetic, loops. We use all of this to put together our programs and make cool stuff. So let's talk more on sorting algorithms because that's what we're mainly interested in. There's a lot: quick sort, merge sort, Tim sort, heap sort, bubble sort, best average. I'm sure you looked at this too, and like if you're in data structures or something like that. But this is kind of like I feel like it's the most important type of algorithm because even though there's like if statements, search algorithms, if your list is sorted right, I mean you don't have to search for it if it's in the right place. You don't need to go looking for it, right? This is on the right, a graph of like the efficiency. That's array size. We'll get into that later. Time complexity and space complexity. Let's look at like an example of selection sort right here. This had to sort a list in your brain. You're probably going to do this, right? Do I have to explain this? Like, if there's six, you find the smallest one, switch it around. If there's a two right there, you switch around with the eight, switch around until it's sorted. Pretty simple, nothing new. And then there's merge sort. This is okay. If selection sort was like how your brain works, merge sort is I like to think it has how like the computer likes like they default to this. It's pretty quick. It's really quick. If you go back here, you can look at that the merge sort worst case is O n log n, which is much smaller than selection sorts n squared, O of n squared. So for how this works, well, it's pretty simple too. Like do this on paper, cut it in half, and then compare 1 3. You'll get how this works. Like put it together and then put this together 1 3 6 8, and then cut it in half again. Cut it in half. Yep, and 4 5 2 7, and then 2 4 5. Okay, it's a little fast, but I'm sure merge sort is a very familiar concept to you guys. Moving on to this, that's kind of what I was talking about. Why we have all of these different uh, algorithms is because there's no like they're not all the same, right? I like to think it's like what's it like making a build for your character, um, or like putting on clothes, right? If it's a hot day outside, you're gonna put light and uh, easy clothes, right? If it's cold outside, you're gonna put on heavy and warm clothes. And I think that's a good analogy. For example, selection sort. Actually, it says here it has one of the worst of n time complexities, which means it's going to take a long time for you to iterate, keep finding this smallest values. You can already tell, like, right, this is going to take a while. You go through the loop again. But if you look at merge sort, I mean, the graphic's pretty slow, but let's look at the chart. It has O of n. Wait, no, that's bubble sort. O of n log n, which is actually the fastest. Except don't look at these. That's weird cases. And yeah, that's kind of why we have it. You want to fit your algorithms to case by case situations. You want to look at what you're doing, analyze your situation, and then find the right selection. I mean, sorting algorithm because Look, selection sort. Okay, I didn't say this, did I? It has the worst big O, but for space complexity, it has a O of 1, which is a constant. That's really good. That that's really good. And for merge sort, if you look at this, even though this is good, space complexity is pretty bad. So which means you're gonna have to make an array here, make another array, make two more arrays, put it together, delete them. It's like a lot of going back and forth. I'm sure like there's workarounds too, but for general purposes, it's going to take more space uh, compared to selection sort, which goes by pretty quick. So I wanted to show like more extreme cases of different sorting algorithms that I liked. This is BOGO sort. I'm pretty sure it's pretty famous. Like you guys know all this. While the list isn't sorted, shuffle the list. It, right? It's pretty simple to use. So use this if you're lucky, I guess. I like it though. Next one is Stalin sort. A little controversy on the name, but basically you can read that. You iterate through the list, and then if it's not in order, just delete it. It's pretty simple. It's pretty nice. And actually, my friend was talking about like if you if you just want like an evaluation of the whole list, you don't want everything, you don't need all the data points. This might be useful. It might be a pretty good option for whatever situation you're in. And this is sleep sort. It's also kind of weird. Um, this is how like this is the steps. The definition for this is sleep for an amount of time which is proportional to the value of each corresponding array element. So what that means is if you have 8 to 9, uh, 8 sleeps for 8 seconds, sleeps for 2 seconds, and then 2 wakes up first, right? So it appends to the list, and then 8 wakes up, yeah, here, sleep 9, of course, and then 8 wakes up first before 9, and then 9 wakes up to wait 9. I'm sorry about the explanation, but like I'm sure y'all kind of get what it does. This is kind of also complicated because it requires multi-threading. So if you want to like practice something like that, I think it's a pretty cool way to flex your skills. But one more thing, good thing about this sleep sort is that you don't need uh comparisons, right? You're not comparing 8 to 2. You're not comparing 2 to 9. It's just like does it by itself. So if that's something you're getting hung up on, I guess use sleep sort. Real quick, there's like a graphic for this I wanted to pull up. Forget it. Never mind. It's too much work. Moving on. This is what I really wanted to show you guys. This also doesn't work. Give me a second, guys. So YouTube blocked my ad blocker, so I need to go to a private tab to do this. You can see this. This is really cool. Um, this is bubble sort. You can see how it works. It's kind of cool. It's like an ADHD trap, but like this video is an hour long, right? And it's titled "Sorting Algorithms to Relax and Study To." Like, who relaxed with it? Exactly. The craziest part, the last time I checked, it had 2 million views. Now it has 2.1. Like, who watched this? Yeah, people like me. But like, even not just for entertainment sake, you can if you look through the video, like this is cocktail shaker sort, optimized cocktail shaker, odd even. I don't even know what gnome sort is. Uh, binary search. I mean, it sounds pretty funky. I don't know if you can hear it. Uh, comb sort. Like, look at how cool that is. I guess it's just me. Wait, I just want to find merge sort because like it's pretty cool. You've watched this whole thing. Yeah, right, right. You just like no, it's an hour. There's an original. I get this is like the remade one. The lore. Okay, stable sort. Okay, see selection sort. You can already tell it only has 128 values, but it's pretty slow. Even for I think this is double selection sort. Like and because double from both sides, still pretty slow. Yeah. If I can just find merge sort. Right? That's what I look for. No, it didn't have any. No, 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 no. I think I looked for them earlier. I probably should have done my prior research, but keep sort, smooth sort, whatever that means. I think it's pretty cool. It's pretty smooth. Mute the stream. No, because like the sound comes from here, and I want them to hear the sound. It's like okay. Okay. This is tournament sort. I don't know what that is. Insertion sort. That's pretty cool. If we can just get to merge binary insertion. I really hope you guys like look this up. This is just kind of like cool. Wait. Shell sort, patience sort. That takes a long time. You can tell. Merge sort, there it is. Look, like other ones, it kind of like goes through, iterates, and like sorts. But like if you look at how this one works, it's like right, it merge sorts like a certain part, merges it, and then sorts this, and then merges that, and then it's gonna merge like the first half, like yeah. It's for your understanding. You can like really tell how these work case by case. So if you have like a situation that like a certain part is sorted, but like you need to look for that, maybe you can use implement merge sort, and it's gonna work pretty swell. Yeah, I don't want to waste too much more time on this. It's called sorting algorithms to relax slash study. Uh, yeah, let's keep going. Okay, so talking about implementing your own algorithms, this is what we're gonna do. 3D printed statues. Some of you might recognize this from the open house. I really like this problem. I made a cool graphic for it too. Uh, so let's read it. Um, you have a single 3D printer, and the goal of this problem is to print n statues, right? But with this printer, because like you're not just gonna like print one at a time, you can print other printers, right? And you can help that one statue to print more statues with other printers. And let's actually get this here. Wait, yeah. So for setting up an algorithm for a problem like this, it's I think it's good practice to do brute force, exhaustive search. That's like a more pretentious name for it, I guess. So you start with one printer. Let's say you have one. How many days is it gonna take to print n statues? N statues. Yeah, n days, right? Yeah, n days. What about two printers? Exactly, n divided by two, and then three printers is n divided by three, and divided by four. And it's easy to tell that the more printers you have, the faster like your days get. Like you can print all the end statues faster. But it's not like we can just like sit here and print printers all day, right? We don't have time for that. So yeah. It's kind of easy to think of it as like iterating through a loop, I think. Um, because as many printers as you have is the speed at which you'll be going through the required uh, statues. So one statue every one printer, two statues every day with two printers, so on. You kind of get it like a for loop with a I plus equals 2 at the end. But obviously you can't just print printers forever. So this, I hope you, if you read this problem, it's pretty easy to realize that when you're printing printers, the printers are going to grow exponentially, right? Because on day 0, you have one printer, and then on day 2, you have two printers, and then on day 3, how many printers do we have? Four. Wait, 4? 8. Yeah, and then on day 4 we have 16 printers, and then we have 32 printers. So obviously printing printers is faster than printing statues, right? So where's the like golden zone? Where do you stop printing printers, and then when do you start printing statues? I think that's kind of like the big catch for this problem. It's difficult to figure out where that is. And again, I think this kind of goes back to Owen. It's not really like that because the whole runtime is just it's not really a loop. But if we think about iterating through the whole statue list with printers, we grow exponentially, right? But with statues, we grow one at a time, which is linear growth. That's an O of n, not a O log of n. If you look back here, when we are growing exponentially, it's this O of log n. Well, n shouldn't be here, but that's kind of what we're doing. I don't if y'all kind of get it. So yeah, this is the equation that I came up with. Days needed is the log base 2 of n plus 2 days because um, you need 2 days to print statues. So how log works is, okay, another tip for these kinds of problems is that you can just like, you have sample cases here, but you can give yourself like a really crazy number, like 100, right? That's not crazy. But if you look back at the list here, how many days is it going to need to print 100 printers? 6.5? 7? 8, actually. Because on day 0, we start with one printer, right? So if we print up to 128 printers, we're still going to need 1 day to print all the statues, right? So plus 1, that's where the plus 2 comes in because O log base 2 of n is actually 62 for 100. So we're going to need 2 days. And that's kind of like an edge case, like at the end there. It doesn't really matter. If you print 64 printers and then for 2 days you print statues, or if you print 128 printers and then print statues for 1 day, that's not going to matter. It's still 2 days increase from 6 or 1 day increase from 7. Yeah. Okay. I'm sure y'all get it. So this is a nice problem. You can just kind of make a graph with this on Desmos. So we can do that 1 or 2 at the end here. It doesn't really matter. But this is kind of how it is. Like this is the D equals the days needed, of course, log base 2 of n graph. And let's say we put like 100 here. If you look at the graph, that's 7.644. So obviously plus 1 is going to be 8. That's 8 days for all the statues. Let me show you the code that I wrote for this because what's going on? other thing that I want to talk about is edge cases. Here it is. Ignore the comment for now. This is the most simple equation that I could come up with. So obviously log base 2 of x. And then this is kind of where it gets confusing. So edge cases. For algorithms, all algorithms, it's going to have edge cases. Whether like if the loop is empty or if the if the list is empty or if there's like one thing in the list, like you're not going to sort that, are you? So it's better to have prepare for those edge cases and like code for them. And this is kind of what happens because it might not be uh, obvious at the start, but because it's simple to think 100, right? And then we go for 6 days and then we print that 64, 64, 128. So it's a little more, right? But what if there's exactly 64? That's 6 days plus 7. Yeah. But 6 days plus 1 equals 7 days. Um, and then for 128, you print for 7 days, all the printers, and then you print for one more day. It's kind of like, so if the number of statues that you need to print n is a power of 2, you don't need to go twice because the log of base 2n is the number itself. So you only print for one day and that's it. So look here. The code is that double D, and if there's so I kind of just like scuffed this. This is supposed to be like D, and you know how we have double numbers like after the point, and then I parsed this into an int and then like subtracted it. So if it's a 0, which means this D is a power of 2, I only add 1. And then if it's not, I add 2 days, and then we obviously that's the answer. Yeah, okay. Yeah, for the second code here, this is kind of like the more general solution, I guess. You just like iterate through and then multiply the amount of printers by 2 here until it's bigger than the amount of statues you need. So this is definitely a more simpler solution to explain, but as an algorithm writer, this is more clean, more basic, just one edge case. So yeah, there's a lot of ways to go about this, and I wanted to show you guys one more here. Oops. Yeah, that's the equation, of course, and boss battle. That's a problem name. Let me actually pull it up. Okay, yeah. This is I kind of want to leave it off as a challenge for you guys, to set it up as an algorithm here. I don't know if y'all have computers or anything. We have donuts here though, if you all want some. Um, kind of explain real quick. Hopefully no one saw that. Boss battle. So we have all these. It. I'm just gonna read it. You're stuck at a boss level of your favorite video game, and the boss battle happens in a circular room with n indestructible pillars. Indestructible. That's pretty important. Pillars arranged evenly around the room. The boss hides behind an unknown pillar. Then the two of you proceed in turns. First, your turn, you throw a bomb past one of the pillars. The bomb will defeat the boss if it is behind that pillar or either the adjacent pillars. So it actually hits 3, the one next to the on the left and the right. Next, if the boss was not defeated, on his turn, he can like either stare where he is or use its turn to move to a pillar adjacent to its current position. So it can move to only like the side that it was in. And the last time you tried beating the, yeah, that's just some context. So we're looking for the minimum amount of numbers, minimum amount of bombs that we need for to catch this ball, to catch the boss and kill him. So this is the sample input, sample output here. Yeah, please give it a shot. We have, oh yeah, yeah, yeah. Cut out the sample input for now. If y'all need it, it's right here. So go ahead. So any ideas on how y'all want to solve this? BOGO story. I don't think that is sorting algorithm for this one. It's much simpler than that. Even though it's not a sorting algorithm, it's easier if you think about it as like you're iterating through the pillars, right? That's kind of a hint. You're going around the room and you're hitting it with the bombs. Uh, yeah. So, anyone other ideas on how to solve this? Yeah, okay. Hmm? Right. It covers three on the left and the right. Yeah. Yeah. Uh huh. Yes. That's a good place to start. So, what would be like the algorithm to get all that? N over two? N over two. Hmm. So half? Two over N? But it's like, you want to think, because you still need, like, if there's a million pillars, do you only need five, 500,000? Because you're skipping one by one. Yeah, yeah. Can you catch up? Uh huh. Yeah. Any ideas? Are we? We are. Two pillars pace. Uh huh. Yeah. This is bad. This is in Bowser. Um. Yeah. 2n over 3. It's much actually simpler than you think. Okay. Let me actually draw you guys a quick graphic. gonna draw here. So let's say there's 1, 2, 3, 4, 5, 6, 7, 9 pillars. Uh, you're bombing this. That's 3, right? It's kind of easier to think of it like this. And then if the boss was here, uh, you want to be able to catch him wherever he goes, right? So if he's going through you, you don't want him to be able to like pass through and like skip you, right? So if you bomb these, he can't be on any of these squares, right? And then you go ahead to bomb these 3 ones. So if he was here, you'll still catch him. And if he's like here, he's like running away, you're still moving faster than him, right? Because you're bombing 3 at a time. And then you're skipping 1. So 3/4. It's much simpler actually. No, no, no. Yeah, it's less than n. No, no, yeah. Mm-hmm. Uh, we are looking for the worst case, the O case. Uh huh. Wait, would it take you 6? Because he can still be moving, right? So 1 bomb, 2, and then 3, 4, and then 5. But like he's still moving with you, right? If he's like moving away from your bombs, the 6th one. Um, the easy thing to think about here is that once you bomb a place, like he can like move to any of your squares, right? But what guarantees is that he can't be here. Like he cannot be there. Because like even if he was here, he could have moved here, yeah, but like he can't move 2 spaces. So he can't be here. That's a guarantee. And when you bomb this, it guarantees these 2 squares that he's guaranteed to not be there. Of course, we're talking about the worst case scenario. So, and then we go ahead to bomb these, right? 8 bombs. Wait, how many pillars are there? 1, 6, 7, 8, 9. 9 bomb. I mean 9 pillars. So what would that algorithm be? So in this case, n is 9. Um, wait, hold up. 1, 2, 3. No. Yeah, go ahead.
So I have it like, let's say worst case scenario he's here, right?
Yeah.
If I bomb here, I take care of these 3.
Uh huh.
And let's say if he's here and I go here, he
Mhm.
goes backwards. So I have
Yeah.
this one as the next guy.
Yeah.
Let's say he's following. So now he's here.
Uh huh.
I bomb these 2.
Yeah.
I move to this guy.
Hmm. And then he moves that way again.
I move to this guy.
Yeah.
He's here.
Uh huh.
Move to this guy.
Uh huh.
He's here.
Yeah.
And then on this one,
Yeah.
I would hit him.
Yeah. So how many would that be?
That would be 1, 2, 3, 4,
5, 6. Is it 7? Is it 6?
first,
Really?
second, third, fourth, fifth, sixth would hit him.
Are we missing something? Okay, I'm just gonna tell you guys the answer is n minus 2. Why didn't you say anything? It is very simple. I'm sorry about that. Yeah, no, it's cool. So the final solution is you can think of it as, okay, actually I have notes for this. Yeah, pretty easy. So throw bomb I to pillar I plus 2, right? Because you want to cover all of your pillars, maximize that. Mod n, where each bomb gives a new position where the boss cannot be. That's what I was talking about, the guarantees. And then when only 3 pillars remain, which means you keep bombing them, moving on, that's a guarantee. Bomb, move on, these are 2 are guarantees. And then this one goes away because you can actually move here and here on his second turn, which means he's following you. And then you bomb this place. That's another 3 that guarantees these 3 spots. So it's kind of it's really difficult to visualize, but when there's only when you keep going around, like this guarantee chain gets longer until there's only 3 spots where the boss can be, and then you bomb the 3 pillars, and then you win. It's it's a little difficult to explain. I'm sorry about that, but it's a nice problem. What is this? Okay, thank you. Um, Example with 8 pillars. Player goes first. Okay, sick. Wait. Oh, thanks. Wait, no, there's it's cool. It's cool. I didn't know it was there. Yeah, it needs water. Okay, can you hold this? Wait. What did I do? Okay, no, I got it. So example with 8 pillars. Okay, so boss starts here. Bomb 1. You bomb these 3. You bomb these 3, right? Yeah. And then boss goes here. And then you bomb these. Boss is here. Bomb these. Boss is here. Yeah. And then you bomb these. He's right here. One more time. Boss is here. And then there it is. The 3 final pillars. And then you bomb the rest. How many was that? 1, 2, 3, 3, 4, 5, 6, 6, 7, 6. Yeah. Yeah. So that's basically the answer. If you simplify it down, like it comes down to n-2. Uh, it's really that's kind of like a brute force solution too, right? You kind of go through, like, have examples, 8 pillars. You could have done 9. You could have done 10. But whatever the case, it comes down to n-2. That's another solution, right? You recognize the pattern and then you make that the algorithm. So, yeah, thank you. I hope you guys make lots of cool algorithms in your CS journey. Oh, by the way, there's donuts here. If y'all want to take some. Can you, like, pass it around?
Or just have them out there so as they're cheap,
Oh, yeah.
they can take it.